Okay, welcome back. So last time we first proved the basic Lyapunov theorem on stability, both on stability in the sense of Lyapunov and then asymptotic stability. We then extended the proof to the case of global asymptotic stability, and we saw that when we extended this proof, we had to add an extra condition which basically guaranteed that the system couldn't drift away as the Lyapunov, the values of the Lyapunov function got smaller and smaller. We then moved to something a little more general when we noticed that if we get back to the basic nonlinear mass spring example, which motivated this whole intuition about Lyapunov theory, we have a small technicality, which is that if we pick the most obvious Lyapunov function candidate, namely the total energy of the system, then if we look at V dot is 0 not only when we have arrived at the equilibrium point, but also every time we change directions. And so we said, well, maybe we can come up with a slightly more general version of Lyapunov's theorem, which will easily handle this case when indeed it's the case that the system tends to 0. And we said basically the idea could be that we will show that whenever it changes direction, it doesn't get stuck there. Okay, so whenever it changes direction, it keeps going, and therefore it does end up at the equilibrium. So that was the motivation for the invariant set theorems, which, as we saw the global version, we'll see the local version today, as we saw were theorems which had a little looser assumptions on what was going on, the existence of a scalar function, and so on, and had also a little looser conclusions, but allowed to play this game more simply. Okay, so we gave. So remember, we had the global invariant set theorem, and we said this theorem one had to wait until the 1960s for these theorems due to Lassalle. So the global invariant set theorem was saying, well, if you can find a scalar function v of x such that v dot of x is always negative and v tends to infinity as x tends to infinity, then all trajectories tend to the set R, which was defined by v dot equals 0. And more precisely, to the largest invariant set within R. So invariant set we define as a set such that if we start there, we stay there. Largest in the sense of the reunion of all possible invariant sets. And within R, because this invariant set had to, trajectories in this invariant set had to stay within R. Okay? And so we gave an example of this. We said, for instance, if we have a scalar system, x double dot plus b of x dot plus c of x equals 0, where b and c are continuous and have the same sign as their argument, then on the very simple extra condition on C, this system is globally asymptotically stable, and so the equilibrium point x equals 0 is globally asymptotically stable. So we said, for instance, if we take an even more specific example, if we take this system, then this system is globally asymptotically stable. In other words, starting with x equal 10,002 and x dot equal 500, it tends towards x equals 0, x dot equals 0. And in this system, we see again that if we just took the linearization of this system, the linearization would be x double dot equals 0. Okay, so the linearization would say, well, we don't know, right? It's a double integrator. But actually, the real second-order system tends to 0 starting anywhere. Okay. All right, questions about this? So we then made a brief remark about the fact that, of course, these same simple results could be used in the control context. Okay. So for instance, we said that if we consider the system, let's say x double dot plus x dot to the fifth is equal to x squared u, right? Where u is a control input to be defined, then obviously if we choose u equal minus x, the closed loop dynamics will be x double dot plus x dot to the fifth plus x cube equals 0, which of course is globally asymptotically stable using this result. Okay. So this is a case where a control input, in this case actually a linear control input, globally make the system tend to 0. Okay. But again, it's not something we could have seen even locally from a linearized analysis, because a linearized analysis is x double dot equals 0, so where we don't even know where there's a control input. Okay. So here a linear control input actually globally stabilizes the system and makes it tend to 0, but there's no way to see that even locally from a linearized analysis. Okay. Now, we said we promised to do a little more example, example based on these ideas. So here, for those of you in the books, we are looking at example 323. I was saying, and we're going to look at this now, these Lyapunov theorems, or extended versions like the invariance theorem, are very simple. The hypotheses are very simple, and you have to be careful that that the hypotheses are precisely satisfied, but very very simple. And also they're all based on inequalities. Things being lower bounded, derivatives being negative, and so on. Okay, so they don't require things to be equal to something. They require things to be bounded. Okay, they're based on inequalities. So because they're based on inequalities, they are very natural tools to study questions of robustness. Okay, in other words, the questions of that saying, well, we have a system model, but the parameters we don't quite know. Okay, we don't know them precisely, and in this case, can we design a controller which, whatever the parameters are, will work, okay, in a certain range? Okay, so to give you a little example of that, we'll do much more sophisticated things in this course to solve these kinds of examples, particularly when we talk about adaptive control. But let me give you a very simple example here. So suppose you have this system, x cube equal u. Okay, so this is your system, And alpha 1 and alpha 2 are unknown constants. Such that, in other words, you don't know what they are, but you know some bounds. Okay? So for instance, this is completely a toy example, okay? You know that alpha 1 is larger than -2, and alpha 2 is less than 5 in absolute value. Okay, so this is your system. You know there are these constants there, okay? So for instance, maybe a mechanical system, and you have uncertainty on the mass, okay, and on other terms. So you have these constants there, and your question is, design a controller that makes the system go to 0 starting from anywhere, whatever alpha 1 and alpha 2 are that verify these properties. Okay? So that's the statement. You have a system, you have the structure of the system, you have some constants. You don't know the constants, you have some bounds on the constants. Okay? Now you see the bounds are not very, are not necessarily very helpful to the stability of the system. For instance, with alpha equal -1, this would blow up, right? Sorry, with alpha 2 equal -1, for instance, this would blow up, and with alpha 1 equal -1, this would blow up as well. Okay, so you cannot say within these bounds the system is nice and stable. Okay, so how could you choose the control law U based on the measured state, position x and velocity x dot, that guarantees that starting anywhere, you indeed tend to x equals 0 and x dot equals 0. Okay? So what's a reasonable choice? Well, it's always the same story, right? We're trying to verify inequalities like this for the closed loop system. Okay? And in a sense, what we want is therefore to create a C of x and a B of x dot for the closed loop system that verify this. Okay? So one way to do this is to choose a control law that contains things like C of x and B of x dot, which are of the right sign, okay? And also which are in absolute value larger than things which may not be of the right sign. Okay? So what's the minimalist version of doing this? Well, okay, so this term could be positive or negative, okay? So we don't quite know what it does. What we would like is something in, for instance, x dot absolute value of x, okay? That would be of the right sign, okay? And so how big does it have to be? Well, at least 5, okay? So not x dot x absolute value of x, right? So how big does it have to be? At least 5, okay? Why? Because if we combine this term with this term, this will give us something of the same sign as this, and therefore a C of x, which is of the same sign as x, right? What about the second term? Well, x dot cube is good enough, except it's multiplied by something which may have the wrong sign. Okay? So what could we do? Well, we can do 2x dot cube, right? We're sure that this term is of the correct sign, okay? And it will be bigger than this in absolute value, right? I'm just saying the closed loop C of x and the closed loop B of x dot have to be of the right sign. Okay? Have to be of the same sign as x. One way to do this is to put in new terms which are of the right sign and just make sure they're bigger in absolute value than terms that you don't know the sign of. Right? So that will work because in closed loop this will anyway dominate this term, and in closed loop this will anyway dominate that term. Okay? Now of course, You could also do minus 10 x absolute value of x minus maybe 3 x dot cube, okay? Or you could do minus 15 x plus x cube minus 5 x dot cube. But these would all work. Okay. And then it depends on how fast you want to go to 0 and what are perhaps other dynamics you haven't modeled and things like that. All right? But you can see on this very, very simple example, you know, that because you have these Lyapunov theorems which are based on inequalities, and therefore you get simple consequences of those which are based on inequalities, okay, then you can very easily handle uncertainty on your system based itself on inequalities. All right, and therefore you can easily handle questions of robustness, okay, to variations in parameters. Questions about that? Okay. So we gave this result here on the global invariant set theorem. There's a local version too, which is a little more technical, which is why we're doing it second. So this local version of the invariant set theorem so remember we said the invariant set theorems were designed, one, to be able to get rid of this problem of v dot being 0 at places where the system has not converged yet. Two, perhaps to explore a richer nonlinear realm, if you want, by being able to show convergence to other behaviors. Not just equilibrium points, but perhaps limit cycles or other kinds of invariant sets. So the local invariant set theorem is very much like the global one, except a little more technical. Okay, so we start with a scalar function v of x in some region omega L defined by v of x is less than some number L. Okay, so we have a region omega L defined by v of x less than L. Okay. The assumption is omega L is bounded. Okay. So that this is a bounded region. Nowhere does it tend towards infinity. So you have a function v of x, you define it by v is less than 17, that region is bounded. Okay. Now, you also assume, of course, that v dot is negative everywhere. So then the result is the same, basically. So let R be the set of points in omega L such that v dot equals 0. then all trajectories, so it's the same result, right? So all trajectories starting in omega L tend to R, and more precisely to the largest invariant set within R. Okay? So the conclusion is the same as in the global invariant set theorem, except everything happens in this predefined region omega L. Okay? Incidentally, we have V dot negative, right? And omega L is defined by V is less than something. So suppose we start in omega L, what's immediately obvious? We stay in omega L, right? Because omega L is V less than something. And V dot can only decrease. So we start, so if we start in omega L, we stay in omega L, right? That's the first obvious implication from this hypothesis, right? But of course, we have this more precise one. Okay? So that's the local invariant set theorem. Okay, so let's now illustrate this. Let's now illustrate this on an example. So it's example 313. So this is completely a made-up example, okay? It's just for you to think about these kinds of questions. Okay, so that's the system. Okay, so you have this system. And the question is, you start at some random initial condition, as large as you want. What does the system do? Okay. So one thing we can already say is that this system has at least one obvious equilibrium point, which is 0. Okay? If x1 and x2 are both 0, the system stays there. Okay? So there's one obvious equilibrium point at x equals 0, but that's not going to be the interesting thing about this system. So suppose you say, well, there's an equilibrium point at x equals 0. Perhaps you try to prove that all trajectories tend towards that equilibrium point, and it doesn't work. So you're trying to see, well, what may happen in the system. So at some point, somebody suggests, and I'm not claiming at all, this was an obvious thing to do given these equations. I just say somebody suggests, because maybe they've seen this example before. So somebody suggests to compute the derivative of this bracket here. x1 to the 4 plus 2x2 squared minus 10. So, you have a helpful friend who's taken the course, and she says, why don't you compute this? You'll see it's interesting. So you faithfully do that, And if you do this, you'll find that you'll get minus 4x1 to the 10 plus 12x to the 2 to the 6 times the same bracket. Okay, now that's reasonably interesting, at least if you're interested in the system. That's reasonably interesting because, well, what could you say? Well, you know, if you keep computing d2 over dt square of the same thing, right? You would also get, well, you would get the derivative of this times this bracket, okay, times this times the derivative of that bracket, and so you would again get something which is multiplied by this same bracket. Whatever order of derivatives you take, you get this, right? That's clear. You get the derivative of this bracket is equal to something times the bracket. So if you differentiate again, you'll get two terms, but each of them, again, will have the bracket in there. Okay? So, under some basic smoothness assumption, what can we conclude from this? What happens if you start with this bracket equal to 0? What? It's not clear that the system doesn't move. So first of all, bracket equal to 0, what does it represent? What does it look like? So we have x1, x2. What is bracket equal to 0 represent? Is it a line? Is it a hyperbola? What is it? I don't want necessarily a name, maybe just a rough name. What does it look like? Well, if it was, suppose it was x1 squared plus 2x2 squared equal 10, right? What would that be? Circle or an ellipse, right? Okay. So it's like an oval, right? It's not x1 squared plus x2 squared. So it's an oval, and if you think about it, it's an oval that looks like this. Okay. It's elongated more in this direction. Okay, so that's this oval here is the system x14 plus 2x2 squared equal 10. And of course, it's perfectly symmetric with respect to x1. So it's not quite this. Okay. All right. So that's this system. So what does this equation say, therefore? So if this bracket is 0, all its derivatives are 0, okay? So basically what it says is that this oval here is invariant, right? Once you're on it, you stay on it, okay? It's an invariant set, right? That's what this says. Once the bracket is 0, then all derivatives of the bracket are 0. Okay? So, that's becoming a little more interesting because it says, for instance, no wonder that you couldn't show that all trajectories tend towards this obvious equilibrium at x equals 0, because if they start on here, they stay there, so they certainly won't tend to 0. Okay? So you might say, well, what's the next guess? Well, the system looks complicated, but not, it's not profound either. Perhaps that's the only thing that happens. In other words, perhaps all trajectories tend either to this oval or to 0. Perhaps we could try to show this. Okay. Now, before we try to do that, let's look at this oval a little more. What happens when we are on it? Okay, so we start on it. We start on this orange curve, right? So we know we stay on it. And therefore, on the oval or ellipsoid, it's kind of generalized ellipsoid, right? What is the dynamics? What can define the dynamics? Well, on the oval, we stay on it, so we need only one parameter, right, to define the dynamics. One quantity to define the dynamics. So can somebody tell me how can we define dynamics? Well, these equations are still true, of course. Right? But we know that the bracket is 0. So it gives us two equations, but we need only one. Right? They have to be consistent. Okay? So the dynamics is given by x1 dot equal x2. First equation. You see that knowing that you stay on here, x1 dot equal x2 will tell you how you move on it. Right? Or equivalently, by the second equation, x2 dot equal minus x1 cube. Right? We agree that we know we stay on the oval, and these equations are still true, of course, but on the oval, the second part is 0. So we have these two equations, but we need only one. Okay? So the motion is defined by x1 equal x1 dot equal x2, or equivalently by x2 dot equal minus x1 cube. Or yet, what's an even, perhaps, even more useful way of defining this? Well, combining these two, right? x1 dot equal x2, x2 dot equal minus x1 cube, right? So if I combine these two, x1 double dot plus x1 cube equals 0. The nice thing about it is just in terms of one variable x1. Right? So all of these are possible ways to describe what happens. Okay? So let's look at the last one, x double dot 1 plus x1 cube equals 0. This system, again, is completely made up, right? It's a mathematical system, but what could be this equation representing? What could this equation represent? If you were given a system x double dot plus x cube equals 0, you would say this could be a mass spring damper with a damping of 0 and a nonlinear spring. Okay? So it's an undamped mass spring system with a nonlinear spring. Okay? And so what do you think if you initialize this system at an arbitrary x1, of course, on this limit cycle, on this oval, right? And you have this x1, what happens is that you have an oscillation in x1, right? The thing does an oscillation in x1. And so what would you call this system? Well, you would call this a limit cycle, right? You have x1 dot equal x2, and the system oscillates in x1. So you see it's going to keep doing this. Okay. So it's a limit cycle. Okay? So everybody understands this so far? We started with this system. There was nothing obvious about it except that 0 was an equilibrium point. Okay? We tried to show that all trajectories tended to 0 because we wanted to move to the next problem. Didn't work. We had the idea somehow to make this computation which showed that this orange gadget is invariant. We looked more carefully about what was happening on this oval, and we noticed that basically all trajectories were going like this, with the projection going like a nonlinear spring, nonlinear cubic spring. Okay? And so, of course, we call this a limit cycle, because that's what a limit cycle is, right? It's going to be this path in the state space that keeps repeating itself. Okay? So, where are we? Everybody understands this? So it also shows you, sometimes it's requires to be a little creative, because, you had to think of, this is more insightful than either of these two, right? But you had to think of putting them together. So what are we now trying to show, perhaps, is that there's nothing more than that going on. In other words, all trajectories either tend towards the equilibrium point or to the limit cycle. Okay? So how might we do this? Well, we can pick a Lyapunov-like or LaSalle function candidate, if you want, V. And try to show with this that indeed we tend to either the equilibrium point or the limit cycle. Okay? So here you can think a little, but in a sense, this computation suggests that perhaps a good candidate would be to take a V which is 0 on this limit cycle and positive everywhere else. Okay, and this is a guess, right? And so this, therefore, one way of doing this is just to take the square of this, right? So if we take the square of this bracket, again, I'm not saying, this is a direct application of the theorem. It tells you to choose this V. We say, well, let's try this. Okay. So what is this V? Well, this is a scalar function, right, which is 0 on the orange oval, right, and then is positive. Okay, so it's kind of a measure of the distance, if you want, to this limit cycle. Sort of measure of the distance. Okay. Now, of course, if we compute V dot, we've done most of the work already, right? Because V dot is going to be equal to 2 times the bracket times the derivative of the bracket, and we've just done this, okay? So if you do this, you'll find minus 8 times x1 to the 10 plus 3x2 to the 6th. Times, again, this bracket square, and you can even, if you like, write this as V. So V is equal to this. If you compute V dot using this calculation, you find immediately that you'll get this times this bracket square, and this bracket square incidentally is V, so you can also write it like this. Okay? All right. So what can we say? Well, of course, what can we say about the sign of v dot? It's always negative or 0, right? Sum of squares and then a positive term and a minus sign, right? Okay? So now, invariant set theorem, let's try to think of the global invariant set theorem. Well, we have v tends to infinity as the state tends to infinity. V dot negative or 0, so we can apply the global invariant set theorem. Okay, perhaps it will give us a useful result, perhaps not, but we can apply it. Okay? V tends to infinity as the state tends to infinity. V dot is negative or 0. So what is the global invariant set theorem telling us? It's telling us that starting anywhere, you're going to tend towards the set R defined by V dot equals 0, and more precisely to the largest invariant set within R. Okay? So V dot equals 0, the set R, right? It's equivalent to what? When is V dot equals 0? Well, V dot is a product of two terms, right? So it's 0 if either is 0. So when is the bracket equals 0? Well, by definition, or from what we just saw, this bracket is 0 by definition if and only if we're on this limit cycle. What's the other and only other way that V dot can be 0? If this parenthesis is 0, right? In English, if we are at 0, right? Sum of squares can be 0 only if x1 is 0 and x2 equals 0, okay? Or okay? So this V dot is always negative or 0. V tends to infinity as x tends to infinity, the state. V dot equals 0 if and only if either we are on the limit cycle or we are at 0. Okay? So if we so that's the set R, right? What's the largest invariant set within R? Or, right? So this is an invariant set and this is an invariant set, right? The origin. So the largest invariant set, which is the reunion, right, is actually R itself. So we don't have to go one more step, right? R is the largest invariant set within itself, right? Because R is, okay? So we don't have to go one more step, but this says, we tend either to the limit cycle or to 0. Okay? We could stop here and say, okay, well, now we know, right? We tend either to the limit cycle or to 0. But we can say actually a little more. What we can say is that actually we tend always to the limit cycle, except if we start exactly at 0. Which of course, physically doesn't mean anything because it's always going to be a small error and so on. So we're going to say, we can say actually, starting anywhere, we always tend to the limit cycle unless we happen to start precisely at 0. Okay? Now, how can we show this? Well, we could try. So that's what we want to show, right? Actually, all trajectories tend to LC, to the limit cycle, unless they start exactly at x equals 0. So how can we show this? Well, we could try to show that the equilibrium point x equals 0 is unstable. Okay. But that doesn't work because actually, you know, if you take the linearization of this, it's marginally stable, so it won't work. x1 dot equal x2, x2 dot equal 0, that's the linearization. So it doesn't work, but we can do actually something more subtle but simpler. How can we show that there's no trajectory that tends to 0? Well, that's one instance where actually the local theorem gives you more information. Okay, will give you extra information. All right? Why? Because suppose that I use, so let's see, I'm not sure if I have space, but suppose we just imagine this just in one direction, let's say the x1 direction, okay? Along this axis, and we plot v. What would it look like? Well, it would be 0 here. It would tend to infinity, right, in these directions. And what would it look like in the middle? Well, it would look like some kind of a bump. And what would be the value of this bump in the middle? I should do a 2D drawing, but it would be very hard, right? So I'm just doing a 1D. Imagine this, right? So you have this plane here, and you have V. Okay, so V is like a sheet that goes to infinity, and there's a bump in the middle. And what's the maximum value of V in this bump? It's at the origin, and it's equal to 10 to the square, otherwise known as 100. Okay. So you see, if you see this, right? The plane x1, x2, you have v going to infinity as x tends to infinity. You have a bump, surrounded by the limit cycle. The maximum value of this bump is 100. It's obtained at the origin. Okay? So actually, all trajectories tend toward the limit cycle unless they start exactly at equals 0. And this can be seen by applying, on top of what we've already done, the global invariant set theorem, applying the local invariant set theorem with what value of L? Remember, it has an omega L. 100, right? Because you see, if we apply the local invariant set theorem to omega 100, omega 100 is defined by v of x less than 100, strictly. So it will, maybe put another, it will contain this entire region, right, defined by 100, which includes the limit cycle. But it won't contain this point, because this point, the value is 100. So in other words, the region defined by v less than 100 is an entire region that contains the limit cycle but doesn't contain the equilibrium point. And therefore, if you start anywhere around the equilibrium point, there's no way you get to it. because v can only decrease. Another way, if you want, of saying that is that v has a local maximum at 0, and v can only decrease. So if you start near 0, you'll get away from it. Okay? So here we use the global invariant set theorem to say we tend towards the limit cycle or the equilibrium point. And then we use the local invariant set theorem, or here equivalently saying that v at the local maximum. We use the local invariant set theorem to say, well, unless you start exactly at 0, all points which are a little away are part of omega 100 and therefore will tend towards the limit cycle, not 0. Okay. So that's the story, and therefore, of course, trajectories look something like this, right? So outside, of course, they tend to the limit cycle, but inside they also tend to the limit cycle. They get away from the origin. Okay. All right. So this is an example where we showed convergence to another kind of behavior, not to an equilibrium point here, but to a limit cycle. And we showed it in a completely global way, right? From this system, starting anywhere, it tends towards the limit cycle, unless you start exactly at 0, which is, probability 0, unless perhaps you have some stiction or something like this, right? Which would be an extra term. Okay. All right. Questions about this? Yes?
Have we proved that starting outside the box, the omega 100, like in the tails of V, that we still tend toward the limit cycle?
Okay, good question. So we first did the global invariant set theorem. So the global invariant set theorem said starting anywhere, including here, we tend to either the limit cycle or the origin. We could have stopped there. We wanted to be more precise. So then we used the local invariant set theorem, which involves this box. But we already know that starting anywhere, we tend to either the limit cycle or the origin. Of course, we cannot cross the limit cycle because it's invariant. Okay? So once we reach the limit cycle, we stay there. Okay? Good question. Any other question?
How do you actually find the invariant set when you are given like a dynamic equation?
Harder to.
I mean, this is
Sure. I think I was fair. I just told you. Suppose you had the idea of, So you can. We'll talk, or at least in some cases you can, but we'll talk about that towards the very end of the course, in terms of transverse contraction and stuff like this. Okay? But it's much harder. You see, the difference with linear systems too, it's not that you give everything to the computer and it spits out the result. You have to think a little either about the physics or about the structure of the things, or you have to play with x double dot 1 plus x1 cubed to understand. You have to think a little more, okay? Which is not bad. Okay? But, so there are ways to go towards this, at least in some classes of system, but they are quite technical. Which is why I said actually the hard part in the proof of the invariant set theorem, which we didn't do here, was to show there was an invariant set, incidentally the existence at least, not even explicitly. Okay. So that's where we are, okay. So we have these extremely powerful theorems. At the same time, they require coming up with a reasonable Lyapunov function candidate, which itself may come from different reasoning about the system itself. Now, of course, in this course, in particular, the first part of this course, we'll see a lot of constructions of Lyapunov functions or Lyapunov-like functions for specific classes of systems, robots and aircraft and things like that. Okay. But in general, there's nothing in the theorems themselves which tells you how to choose these Lyapunov functions. Now, it turns out, not surprisingly, that for linear time-invariant systems, you can very systematically find Lyapunov functions that they are stable. So you might say, who cares, right? For linear systems, I don't need all that stuff. And you would be right. Okay. So why would we be interested in this? Well, first of all, just philosophically, because it kind of gives a common language, to talk about both linear systems and nonlinear systems. But more practically, because as we will see in a variety of ways, just like energy, Lyapunov functions combine. Okay, so if you build Lyapunov functions for systems composed of parts, you're very often going to obtain them by just adding the corresponding Lyapunov functions as you would add energy. Okay. And so there's nothing that says that you're not allowed from now on to use a linear low-pass filter, or you're not allowed to use a PD controller or something like that. So it would be nice if, at least for the linear parts, they came automatically with a Lyapunov function subblock. Okay? So that's, from a practical point of view, that's the main motivation. If you have a nonlinear control system with some linear parts, okay, at least with the linear parts, you don't have to think about where could I find a Lyapunov function. Okay? And then you'll combine them, you'll add them to the other parts. So that's what we want to do. Okay, so Lyapunov analysis of linear time invariant systems. As you know, often linear time invariant is abbreviated as LTI. Okay, and so x dot equal AX. Okay. So before we do this, I'd like to do a little brief review on matrices. I might need the whole board. So some very basic matrix algebra. Yeah, that's fine. That's fine. You can just stay. Some basic matrix algebra. So first of all, so if we consider a constant square matrix, M. Okay, so this is a brief review of matrix algebra before we look at this question explicitly. So this matrix is symmetric, said to be symmetric by definition, if M transpose is equal to M. Okay, so basically if you flip it around the diagonal, you get the same matrix. Okay. It's said to be skew symmetric if M transpose is equal to minus M. Okay, so if you flip it around the diagonal, you get minus the matrix. So for instance, you can think of a matrix 0, 1, minus 1, 0. Okay? Okay, and important point, skew symmetric is not the contrary of symmetric. Okay, the contrary of symmetric is not symmetric. Okay, so skew symmetric is something else. Okay, so any square matrix M can be written, that's a trivial algebra, as M plus M transpose over 2 plus M minus M transpose over 2. Right, that's obvious because you get M over 2 plus M over 2, which gives you M, plus M transpose over 2 minus M transpose over 2, which gives you 0. Okay, so that's obvious. Okay. Now, why am I writing it this way? What can be said about this first matrix, M plus M transpose over 2? It's symmetric. And of course, this matrix is skew symmetric. If you take its transpose, you get minus the matrix. Right? So any square matrix can be decomposed actually uniquely into the sum of a symmetric matrix, M plus M transpose over 2, and a skew symmetric matrix, m minus m transpose over 2. All right? Okay. Now, suppose M is skew-symmetric. And we take an arbitrary vector x, and we compute x transpose mx. That quantity, of course, is a scalar. So it's equal to its transpose, right? The transpose of 2 is 2, right? But it's also the transpose of a product. So remember, the transpose of a product is the product of a transpose, but in reverse order. Okay? So it's a scalar, so it's equal to its transpose, okay? What's the transpose of this? Well, it's x transpose, the transpose of this term, times m transpose, the transpose of this term, plus x transpose twice, right? So x. All right? So this scalar, if you take its transpose, you get this, which is the same thing as this scalar. But of course, we assume that m is skew-symmetric, so we can write this as x transpose mx with a minus sign, because we assume that m was skew-symmetric. Okay? So for an arbitrary vector x, x transpose mx is equal to minus x transpose mx. In other words, it's equal to 0. Right? So if m is skew-symmetric, for any x, x transpose mx equals 0. Okay? And we can show, it's very easy, it's in the book, you just have to take the basis vectors, but it's actually true, and the sum of 2 by 2 of basis vectors. The converse is also true. So in other words, if you have a square matrix such that for any x, x transpose mx is 0, then it is skew-symmetric. Okay, we haven't shown this here, it's just a few lines. Okay? So if you have a square matrix, saying it's skew-symmetric is equivalent to saying that for any x, x transpose mx is equal to 0. Yes?
Shouldn't the middle part be x m transpose x transpose?
Sorry? This?
Yeah, the middle part, shouldn't the first x instead of x transpose be x?
No, because remember it's the product the other way around. The product of the transpose the other way around, right? So the transpose of x, that's x transpose. We start with that, right? It's m1 m2 transpose equal to m2 m1 m2 transpose m1 transpose. Okay? All right. So if m is skew-symmetric, it's obvious then this is 0, and it's very easy to show that the converse is true as well. Okay. So what does this imply, by the way? It implies that if you take a quadratic form, in other words, if you take an arbitrary matrix M and compute what's called a quadratic form, in other words, for an arbitrary vector x, the scalar x transpose mx, right? This M can always be written as the sum of the symmetric and the skew-symmetric part. So let's call this M sim and m skew, right? So it's x transpose m sim plus m skew times x. And we know that the m skew part will give us 0. Okay, so it just gives us x transpose, the symmetric part, times x. So if you have an arbitrary matrix M, square matrix M, and you compute x transpose mx for an arbitrary x, it's the same thing as computing x transpose symmetric part of M times x. Right? Only the symmetric part matters, okay? So which also says if you want to consider a general quadratic form X transpose Mx, as general as you can always assume that M is symmetric because you know the skew symmetric part won't help, won't change anything. Right? So if you consider a general quadratic form, you're not more general by saying I consider an arbitrary square matrix M. You might as well pick M symmetric. Yes?
Does that affect the eigenvalues of the system then? If you decompose it into the symmetric and skew symmetric?
Oh yeah, of course, the eigenvalues are going to be different, right? The eigenvalues, the two parts are going to be different. Now remember, since you're mentioning this, for a symmetric matrix, which is why, one of the reasons why this is a nice thing to remember, right? That only the symmetric part matters. For a symmetric matrix, okay, composed of real elements, okay, all eigenvalues are real, okay, and all eigenvectors can be chosen orthonormals. Okay. Right, so they can be chosen orthogonal, and you can make them orthonormal by normalizing them. Okay? So a symmetric matrix is always diagonalizable, all eigenvalues are real, and all eigenvectors are orthonormal. Okay, which implies, this second part, of course, implies it's always diagonalizable. Okay. So, continuing on brief reviews of matrix algebra. So, the square matrix M, not necessarily symmetric. So some authors assume it's symmetric. Doesn't matter because of this property, but here we'll just assume it's an arbitrary square matrix. So a square matrix M is said to be positive definite. Positive definite, which we will denote this way, M positive. If X transpose Mx is strictly positive, unless X equals 0, in which case, of course, it's 0. So a matrix is positive definite by definition if and only if, sorry, no transpose here. When you take the quadratic form X transpose Mx, you get a strictly positive number, whatever X is. Okay. Incidentally, remember we talked about a positive definite function, right, when we talked about Lyapunov theorem. And a positive definite function was a function which was 0 at 0 and strictly positive everywhere else, okay, locally or globally. So we could also say M is positive definite if and only if the quadratic form is, let's say, is a globally positive definite function. Right, we say a positive definite function is a function which is 0 at 0, is strictly positive everywhere else, locally or globally. So a matrix is positive definite if and only if the corresponding quadratic form is globally positive definite. Okay, this is not much insight, right? It's just playing with definitions. Okay. Now, geometrically, what does it mean that a matrix is positive definite? Or that's at least what's one simple interpretation of saying that a matrix is positive definite. Yeah, the eigenvalues are positive. Yes, we'll come back to that, but geometrically. And actually, not quite. If it's symmetric, the eigenvalue is positive. Otherwise, we don't know. Okay, the eigenvalue of the symmetric part is positive. Yeah, but geometrically. So, using mathematics considerably beyond the scope of this course, we can write X transpose Mx as X transpose Mx. Right. And if we do that, then we see that X transpose Mx can of course be interpreted as the dot product of X and Mx. Right? That's X transpose Mx. Right? So saying that a matrix is positive definite, saying that whatever x you take, the dot product of x and mx is always positive. In other words, that this angle in some n-dimensional space is less than 90 degrees. Okay? So saying that a matrix is positive definite says that if you take any vector, mx makes an angle with x, which is less than 90 degrees. Right? Now you can even guess now why this is going to be important, because remember we had this condition on c being the same sign as x and b the same sign as x dot when we played with simple mass spring damper systems, right? This condition says that basically mx and x are kind of pushing in the same direction. They live in the same half world, right? So in a sense, that's what's going to replace sign conditions in the scalar case, right? It will have to do with kind of positive definiteness of matrices, at least in simple instances. Okay, questions about that? So two last properties, okay? So for any x, remember we're going to play with Lyapunov functions and bounds, right? So X transpose Mx, the matrix M, if it's not symmetric, is not necessarily diagonalizable, but its symmetric part is, okay? So we know that X transpose Mx is equal to X transpose M sim X. So that's diagonalizable. And so it's easy to show that we know it's diagonalizable. We know it has real eigenvalues. These eigenvalues we can put in a string, right, between lambda min and lambda max, all the real eigenvalues of the symmetric part of M. And so this quantity will be less than lambda max of the symmetric part of M times x squared and lambda min of the symmetric part of M times x squared. All right? So if you have X transpose Mx, the scalar, you can always bound it by taking the symmetric part, computing the eigenvalues of the symmetric part. They are all real. There's a biggest one and the smallest one. Okay? This X transpose Mx is less than the biggest one times square norm of x, and is larger than the smallest one times square norm of x. Okay? And finally, if M is symmetric, otherwise you take the symmetric part. It's very easy to show actually using this result that M is positive definite if all its eigenvalues are strictly positive. Okay. Otherwise, you take the symmetric part and all the eigenvalues symmetric part are strictly positive. And there's also another criterion, which, by the way, should remind you a little about the Root-Hurwitz criterion in flavor, which says, suppose you have a symmetric matrix M. One way to find out if it's positive, definite, is to first look at this left corner term, and this left corner term has to be positive. Then you look at the 2 by 2 determinant that follows. So this is a 2 by 2, and that determinant has to be positive. Then you look at the 3 by 3 determinant, and that determinant has to be positive, okay, all the way to the n by n, determinant of the whole matrix. All right? So that's a standard result in algebra, technical result, right, which says if you have a symmetric matrix, if you don't, you start by taking the symmetric part, and you want an algorithm to find out whether or not it's positive definite, then one algorithm is to say, well, the upper left corner has to be positive, has to be strictly positive, the 2 by 2 determinant has to be strictly positive, and the 3 by 3 determinant has to be strictly positive, all the way to the determinant of the whole matrix. Okay, that's a necessary and sufficient condition for a symmetric matrix to be positive definite. Okay. And you see these kind of explicit conditions, for instance, can be useful for robustness because they could depend on parameters and they could give conditions on parameters, for instance. Okay. Any questions about this review on the matrix algebra? All right. So in the last 5 minutes, we're going to start talking about this. Well, it's 3 minutes. We're going to start talking about this Lyapunov theorem. So we have a system x dot equal ax. And in the case that it is stable, we'd like to be able to show that we can come up with a Lyapunov function. Okay? And of course, since mathematics are supposed to be consistent, we know that we won't be able to come up with a Lyapunov function if it's unstable. Okay? But we'd like to be able to show it in the case it's stable. So we have a system x dot equal ax. And so as a Lyapunov function candidate, we're going to consider a quadratic form, x transpose px, where we have a constant p matrix, which is symmetric and positive definite. So that's our candidate. If we compute v dot, we have a product of 3 terms. So we have x dot transpose px plus x transpose p dot x plus x transpose px dot. And of course, x dot equal ax. So x dot here is ax. P dot, of course, is 0. So I simply get x transpose A transpose P plus PA times x. Okay. So this is our Lyapunov function candidate. This is what its derivative is. We're going to call this quantity minus q. And the game is going to show, to show that we can, if A is indeed strictly stable, if the system is strictly stable, then we can indeed find a positive definite matrix P and a positive definite matrix Q, such that this condition, A transpose P plus PA equal minus Q, is verified. If that's the case, then we'll have found a globally positive definite function whose derivative is globally negative definite. The function V will tend to infinity as x tends to infinity, and so we'll know that the system is globally asymptotically stable. Okay? So that's where we are. That's what we'll do next time, to show how, for a system like this, when it's stable, we can indeed find a positive definite matrix P and a positive definite matrix Q, such that this definition, A transpose P plus PA equal minus Q, is verified.